In this session, we are going to derive the dynamics of one DOF manipulator with uniformly distributed mass using Lagrangian Euler method. So let us draw the single link manipulator. So let us take this as our reference frame. So this is y-axis and this is x-axis. So let us say the link of length L, it is having an angle theta relative to the reference, right? So here, as being this distributed mass, we need to find the kinetic energy and potential energy for a smaller element first, and then we have to integrate it over the entire length, capital L, right? So let us see how to get it. So let me take a point Q, which is at a distance, say small l from the origin or the reference, that is, this is small l, right? So the coordinates of the point Q, the position of point Q will be L sine theta. So this distance, right? So this is your X. So this distance will be L sine theta, comma. So this is in the negative direction. So this side it will be minus L cos theta, right? So if this is the position, then the velocity will be L cos theta theta dot, comma L sin theta theta dot. So to derive the kinetic energy, we need V square. So V square will be equal to L square theta dot square, right? So we are deriving the kinetic energy for a small element. So let us say dl. So the small that is dk, the kinetic energy over the small element that is denoted as dk. dk will be equal to half into mass of the rod. So mass of the rod will be density times the length, right? So dl into v square, that is l square d dot square, right? So this is the kinetic energy of that is associated with the smaller element dl, right? Now in order to get the kinetic energy for the entire link, we need to just integrate this over the length of the link. So we'll be getting the kinetic energy k by integrating dk over the entire length, that is from 0 to L. So we'll be getting integral 0 to L half rho L squared theta dot square dl. So that will be equal to half rho. So differentiating is, or integrating with respect to L. So this will be L cube by 3. So applying the limits from 0 to L into theta dot square. So we'll be getting, after substituting the limits, we'll be getting 1 by 6 rho L, sorry, this should be capital L. So the limit after substituting the limit, this will be L cube theta dot square, right? So here we can say the product of density times the length will be the mass of the rod. So this we can represent it as 1 by 6 capital M L squared theta dot square. So this is the kinetic energy of the rod, right? So next we will derive the potential energy. So the potential energy of the element dl will be, the element dl will be equal to, say, dp will be equal to, again, the mass, so which is rho into dl into G into H. How will you find the height? So here we have already seen this is the length. So and we have taken a point Q in here, right? So this distance it is, if this is theta, this distance will be for a small length L, this distance will be L sin theta and this is L cos theta, right? So this is the height. So this, so if this is the line of reference of potential energy, so this distance will be your height, right? So this distance will be your height. So how will you get this height? So height will be equal to the total length, as you know, the total length of the rod, it is L. So the total length L minus this distance, that is L cos theta, right? So L cos theta. This is your height. So this is the potential energy for a small region. So it is dP. Now in order to get the total potential energy of the rod, we need to integrate it over the entire length. So 0 to L dP will be giving you the total potential energy P. So what do you get? And by integrating, you will be getting integral 0 to L rho G L minus L cos theta into dl. So rho G and capital L, it is constant. So you'll be getting rho G L square minus rho G L square by 2 constant, right? So as we just you know, rho G LDL. So LDL, when you are integrating, it will be L squared by 2. So when you just apply the limit L, you will be getting rho G L squared by 2 cos theta. So that is how you get this term, right? So should I just detail it? So let me just do that here. So the integral 0 to L rho G L dl minus integral 0 to L rho G L cos theta dl. So this, when you just integrate, it will be simply rho G L into L, applying the limit 0 to L, right? Then minus rho G L cos theta into L dl. So L dl, when you just integrate, you will be getting L squared by 2 and applying the limit 0 to L. So when you just apply the limits, you will get the potential energy P as we have got it here, right? So we have got the kinetic energy and potential energy. Now we have to get the Lagrangian, so which is K minus P. So we have the kinetic energy 1 by 6 m L square theta dot square minus the potential energy. So it is rho G L square plus mg by 2 L cos theta, right? So the dynamic equation, when you just get dou L by dou theta dot, then dou L by dou theta, right? So dou L by dou theta dot. So as you see here, only this has theta dot. So on differentiating that with respect to theta dot, we'll be getting 1 by 3 ml square theta dot. And then differentiating with respect to theta, you'll be getting dou L by dou theta will be equal to mg by 2 L. So it is minus sine theta, right? So we have the torque equation. Tau is equal to d by dt of dou L by dou theta dot minus dou L by dou theta. So with that we'll be just substituting, we'll be getting, as we have dou L by dou theta dot is 1 by 3 ml squared theta dot. So whereas d by dt of dou L by dou theta dot becomes 1 by 3 ml squared theta double dot minus dou L by dou theta. So it will be, so here plus here. So mg by 2 L sine theta. So for this is the dynamic equation for a single link manipulator with uniformly distributed mass.